In this work, we study how to adapt pre-trained foundation models to new non-standard sensing modalities. We focus on single-photon imaging as a representative case and propose a noise-aware adaptation framework that explicitly accounts for acquisition-induced appearance variations. Many emerging sensor modalities show similar geometric structure with RGB images, making pre-trained vision models a natural starting point. However, data in these modalities is often limited, and imaging conditions such as noise or photon statistics can strongly affect appearance. As illustrated on the right, the same thing can appear very differently under different acquisition conditions, even though the underlying semantic structures remains unchanged. This entanglement between semantics and imaging conditions makes it difficult to learn robustness implicitly from data alone. This motivates us to explicitly condition adaptation on imaging statistics rather than relying on large-scale data to learn these variations. Our framework starts from a frozen pre-trained video encoder. As shown in this figure, we first extract noisy embedding from raw single-photon measurements, which summarize the underlying acquisition conditions. Then, a lightweight noisy adapter uses these embeddings to condition feature modulations, adjusting pre-trained visual features based on the imaging conditions. This produces noisy-aware representations that can be effectively adapted for downstream classification with very limited label data. We find that the learned noisy gates correlate with how sensitive different feature dimensions are to imaging conditions. This suggests that the adapter identifies condition-sensitive directions in the pre-trained featured space. We leverage this observation to design gate-guided feature-level augmentation, where the learned gates indicate how features should vary under different imaging conditions. This behavior is reflected in the realization on the right. Very well, feature variations induced by our GGFA align well with the true imaging variations compared to the imaging level augmentations such as the random erasing or add some Gaussian noise to the input images. We evaluate our methods under fuchsia setting across multiple different pre-trained backbones, such as the different versions of the clip and different versions of the dinos. As seen in the figures, the noisy adapter consistently outperforms strong adaptation baselines, particularly in some low shot regime. These results demonstrate that explicitly conditioning acquisitions statistics leads to more robust and data-efficient transfer. In summary, noisy-aware adaptation enables effective transfer of foundation models to new sensor modalities, particularly for some physical-driven sensing modalities, such as the single-photon LiDAR. By explicitly conditioning feature modulations on acquisition statistics, pre-trained representation become more robust to imaging variations in data-limited settings. The code and implementation details are shown in this link. Okay, thank you for watching.